Hello, curious people. This is applications of Newton's laws. We already learned about Newton's laws. Now we are going to learn how do we apply it to questions and problems in the world. This one is specifically about stationary equilibrium situations, not nearly stationary, equilibrium, and we'll get to that. Objectives here are: 1. Draw and make an effective use of free body diagrams. We already practiced them. We'll draw them, apply them to questions. Recognize and solve simple equilibrium problems. We'll get to the equilibrium and what it is and solve problems. Distinguish mass, weight, and apparent weight. We did touch base on that already, and we'll apply it to problems. Use simple model of friction and drag. Apply the full strategy for force and motion problems in a single particle dynamics. Remember, we were imagining people to be particles. And understand how to apply Newton's laws to interacting objects. So what is equilibrium? Equilibrium is when we have a system that has zero net force. This sign here is means like sum. Total is the Greek letter sigma. When we talk about total or a net value, we use this. So this means total force. Or net force, because when we add forces, they are vectors and they could actually be in opposite directions, cancels each other. We'll see that. But the idea for equilibrium is acceleration is equal to 0 and F net is equal to 0. That's the main takeaway here. How we're going to solve the problems is same approach. Draw and ugly pictures would be draw free body diagrams, right? Pictures. Imagine the situation, what's going on here. Then if we have equilibrium, we'll apply equilibrium situation. F net is equal 0, adding all forces will be 0, acceleration will be 0. And we will actually use a very simple approach here, and very useful approach. Total forces up are going to be equal to total forces down, because force is a vector, and since force is a vector, if net force is 0, they should all cancel each other when we add them. So up forces will be equal to down forces. Similarly, total forces left will be equal to total forces right. Alright. This is also the same thing. So in a 2D situation, you can say total Fx is 0, total Fy is 0 if we have a total force 0. Now acceleration 0 means another important feature here is acceleration 0 means doesn't necessarily mean the object is stationary, which I said by mistake initially. It means object either is stationary or moving with a constant speed. Remember, if we have a constant speed, acceleration is also 0. And Newton's second law tells us that F net is always equal to the total mass times the acceleration. So if this dude is 0, this dude must be 0. And mass, of course, cannot be 0. And I'm gonna actually teach you this through problems, directly problems. Here are simple equations. F net is 0 because acceleration is 0. Total forces left are equal to total forces right. Total forces up are equal to total forces down. And this comes from the fact that we apply that along x and along y separately. Total Fx is 0. Total Fy is 0. And let's now apply them. First question we have here. A person is pushing a lawnmower, mowing his lawn. And the force he applies is 100 Newton. They already have an ugly picture for us here, so we are good. A person pushes a 20-kilogram lawnmower. So the lawnmower has a mass. I'm going to put it here. 20 kilogram. At a speed of, with a force of 100 Newton. We put this down already. And the handle is at an angle of 35 degrees. So that gives us, I'm going to actually draw it from here. Let's go back here. It makes more sense to draw it from the center of the wheel. Here is the application direction of the force, and this angle is 35 degrees. Alright, draw a free body diagram, which is already drawn here for us. A. We have a force applied by the person. I'm going to redraw those forces for you folks. This is the force applied by the person. 100 Newton. Friction is ignored, not said in here. Nobody says friction is ignored, so there will be a friction force. Since the lawnmower is moving, it will be a kinetic friction. We call these Fk, so let's go ahead and call them Fk here. This picture gave them a different name, but I'm gonna name them with the names we like. This is F, the person applied 100 Newton. Let me do a better job here. And there will be a normal force. I'm gonna use blue for that. Upward, always perpendicular to the surface, right? They used Fn for that. It's not a big deal. We use small n. Our book uses small n. Here are all the forces. Yeah? No. There's one more force I'm gonna show with red. It's also shown in here. Is the mg, or the weight force. Always down, and it's always there if we are on a planet. Or the weight. This is our free body diagram. I followed the approach they used. We could also draw this. I like carrying all the forces to a point in the object of interest, and imagine my coordinate system there. So I'm gonna draw the kind of the wheel of my lawnmower, and I'm gonna draw all the forces in here. I know the guy is pushing in this direction, so that will be the force applied, and I am imagining my XY system. I'm gonna do that with maybe black. They showed an XY system here. You see, I'm gonna imagine my XY system right in the center of this wheel. So I'm kind of drawing a picture together with particle model. Again, this is how I like it. It helps me imagine what's happening here. Imagine my coordinate system. This is my X, right in the point where the stuff are happening, where the action is happening. And I like carrying all the forces in that point, imagining them there. You can move them around a little bit. You'll see I'm also going to be doing this, but I'm going to put them close by to help me. So this force applied along this direction, let me use yellow for that again. Along this direction, I'm going to carry it to here. That's the force, and it will help me see how that force works. This is the force F, 100 Newton force that the man applies. This angle was 37. So this angle, these are inverse angles, called inverse angles, and they're always equal to each other. So this angle will be 37. Right away, I can imagine this guy will have an X component positive, Y component negative. This helped me already. I'm going to show the friction force, which we applied to where my lawnmower is touching to the lawn. So I'm going to show it right here, but I'm also going to imagine that I can carry that. Remember, the vectors can be carried in any position we want them to be carried without changing the, I'm going to use a different color here actually. Let's use green. Without changing their length or direction or magnitude or direction. This would be the friction, kinetic friction. It's moving. Let's do that too. And I'm going to call this Fk. It's to the left, so I can imagine it here. So it would be along a negative x direction, right? And what else I had? I had mg, and I'm going to carry mg here too. Now the reason I wanted to put the friction on the floor, because it is on the floor always. And I carried these other forces to the center of this wheel. And now I can see I have an x component to the right, again y component down, and I have all my forces. Except I forgot to add the normal force. Let's also add that. Normal force is always perpendicular. It's applied by the surface again, so I'm going to draw it from the surface. It's kind of a mixture of carrying everything to a point and drawing on the picture to help me see what's happening here. Use your own method. I've seen some of you just drawing a point in the origin and showing all the forces there. It's all good. If you want to imagine situation a bit, what's happening there physically, you can draw this. But what we do eventually is to carry all the forces to the origin, which should be this one here, and find the total force. That's my free body diagram. B tells me calculate the friction. I'm going to redraw forces here. Again, they're already on the picture. But I have my friction to the left, Fs. I have my force in this direction, F, 100 Newton. And I set my XY system, imagine my XY system right on my object. And I found this angle to be 37 degrees. Let me draw one of these with a different color actually. Okay. Alright, I'm gonna start over here and choose to use direct line, which will look better. So this is the force applied, this is the friction force, and normal force is here upward, and we also have mg down. Imagining my XY system to be here. Everybody is either up, down, right, left, except for the force F. So I'm going to find the components of that force. Angle, I decided that it's 37 degrees. This is my F, and it's 100 Newton. Now, one important thing said here that I skipped before is that the lawnmower is pushed with a constant speed. Constant speed means A is 0, and A is 0 means the system is in equilibrium, F net is 0. So here I'm going to start with that. A is 0, F net is 0, because it's equals to MA. And the clue that gave me this information is that the lawnmower is moving with a constant speed. Oh, speed. Constant. Alright. So constant speed, no acceleration, no force. That means this situation holds. Along X, we have 0 total force, so forces to the right are equal to forces to the left. Along Y, we have 0 total force, so forces up are equal to forces down. Now I am looking for this guy, F kinetic. It's to the left, and there's no other force to the left. And forces to the right. This guy is mg, by the way. Let me redraw it. Let's make it red. This is my mg. Mg is down, and normal force is up. Small n. Let's put small n. N. Sorry about that. And my force F has 2 components. Let's show them in blue. One is Fx. I'm gonna go fast here. I'm not gonna draw lines and then find where they hit the x-axis. We already know that. So I'm going to directly draw the x and y components overall, approximately, showing their direction. Y component is down, x component is right. Now I'm looking for friction force. So using horizontal condition, total Fx is 0. Forces right, shorten that, equals forces left. Shortcut here will give me that. Forces in the left direction is only Fk. Let me actually turn that around. I will say it as forces to the left, which will be more instructive. Forces left direction equals forces right. The same thing, just rearranging. And forces left here, Fk, kinetic friction. Forces right as Fx, x component of F. Alright? And I'm done with part B, almost done with part B. All I have to do is find it Fx. Fx is equal to F cosine 37. It's 100 Newton times cosine 37. In previous lectures, we learned that the unit for force is Newton, and we use capital N for that. So get comfortable with that. Once we do that, we're going to find Fx to be 79.87 Newton, and that's exactly what my friction, kinetic friction force is, 79.87 Newton. How did I find it? Forces to the left are equal to forces to the right. Alright, that's B. C, calculate the normal force. Calculate the normal force. Now I'm going to show all the forces again to make this clear. Imagine my origin here, let's say. I can put my origin anywhere I want, remember? And we said we have Fx and Fy down and right. Right and down. We have F in this direction. This is 37. We have mg down, weight, right? That's weight. I always use mg for weight directly. So I'm carrying everybody here. F friction to the left. Kinetic friction, normal, force to up. Again, they call it Fn. We call it N, doesn't matter. Now we're looking for this guy. We still have equilibrium. Still A is 0, F net is 0, right? This is the same system. And I'm going to use total Fy equals 0 here. Why? Because normal force is up. And I'm going to use that forces up are equal to forces down. So forces up equals the forces down. What does that give me? Notice here, I have only normal force up. Good. Down, I have y component of F and mg. So I'm gonna say my up force, only one force, normal force, is equal to down forces mg plus Fy. So when I add them as vectors, I'll get 0. What would that give me? Let's calculate Fy. Here, let's say Fy is F sine 37. And that's equal to, well, let's put in some more numbers for you folks. 100 Newton is F times sine 37 degrees. And that will give me 60.18 Newton. Okay. Mg, 20 kilograms was the mass. Let's remember that. Question told us that the lawnmower had 20 kilogram times 9.8 meters per second squared. That's mg. That actually I'm quickly going to do. I don't have it written in here. Let me hide this dude and get to my calculator. So I'm doing 20 times 9.8. And 196 Newton will be my mg, weight of my lawnmower. So 196 Newton. Then my normal is equal to 60.18 Newton plus 196 Newton. Let's also look at that. So I'm going to add what I found here to plus 60.18. And 256.18 is my normal. 256.18 Newton. Let me check that again. Yes. That's equilibrium. Up forces are equal to down forces, right forces are equal to left forces, generally gets us there. And this could be the hardest you get from the equilibrium questions. Generally, either the system will be moving with a constant speed, like in this case, with constant or stationary. In both cases, A is 0. F net is 0. Up forces are equal to down forces. Right forces are equal to left forces, gives us the answer. Other questions are all similar. For example, here in this figure, we have 4 different equilibrium questions with tension. Remember, tension is constant. Constant along the same rope or string. And it has 2 directions. It's stretching the string. It could be up and down here, depending on which system I am looking at. So we're going to use equilibrium to find all these tensions. Values are already given here. Tension here is 100 Newton, 50 Newton, 33.3 Newton, and so on. How do we solve this? If the system is in equilibrium, I'm going to show all my forces. And of course, each of these masses has a weight, mg, and it's actually given as Newton. Alright, so 100 Newton down. Mg is equal to 100 Newton for all. And I am actually trying to lift this mg, this weight, which is 100 Newton. With different systems, as this is actually used in life, I can apply a lot less force here to lift the system, depending on how I built them. In the first one, I have to apply 100 Newton, second 50, third 33.333, and the last one is the best one, 25 Newton. I can lift it 100 Newton system. These are called system with okay, great, I forgot the name. Pulley systems, system with pulleys, and they are again used in industry a lot. And I will find the tension depending on wherever I'm looking. I'm gonna cut my small system. So let's assume I'm just looking at the system below this here, or I'm looking at the forces applied to the mass, this mass here. Weight is down, tension is up for this mass. Okay, and the tension I'm going to call it T, and the mass is stationary. Okay, or the system is in equilibrium. It could be stationary or moving with a constant force or a constant velocity, or moving up or down is fine, up with a constant speed. Again, when I say speed, I mean the magnitude of velocity. It could be up or down. In either case, A is 0, F net is 0. Okay, F net is equal to ma, Newton's second law. And then I say, okay, if F net is 0, I only have up and down forces here. I'll say up is equal to down. And by up is equal to down means I mean forces up are equal to forces down. So tension is equal to mg equals 100 Newton. Here I'm lifting up this guy and the mass down with 2 ropes. I'm going to cut it from here, and I'm going to ask you folks to ignore the stiff part here. Just look at the masses. Another thing we are ignoring here, this is also important, and we always will do it. We won't complicate the systems that much. Ignore friction and masses of the pulleys. Okay, we use light pulleys generally, and even if they may not be negligible, we will neglect them. So ignore the pulleys mass or weights and friction between the rope and the pulleys. Look at the tension here. I have tension up and up, 2 tensions up, and they are the same T because it's the same rope along. So I have 2T up. What I have down is 100, so I'll say up is equal down. Let's say F up is equal to F down, so you guys will remember forces up are equal to forces down. Then I'll have 2T is equal to 100 Newton, so T is equal to 50 Newton. Here's I have my little guy giving you a thumbs up. Remember, tension is the same through the same rope. Third situation, I'm going to cut from here. Okay, now I have 3 tensions up, T and T and T, 100 down. So for the third one, let's divide these actually. For the third system, I have 3T is equal to 100 Newton. So T is equal to 100 Newton over 3. Okay, up is equal to down again. I got a shortcut here. I hope you guys are fine with that. Fourth one, they kind of cut it for us as well here. I have 4 T's up. Again, I am ignoring the stiff addition here. It's solvable, but you guys are not going to worry about that. Only look at the ropes. Total ropes up 4. So I have T plus T plus T plus T. 4 T's up are equal to 100 Newton down. And T is equal to 25 Newton. That's a pulley system in equilibrium, and that's how equilibrium works. And here is the main idea you guys need to know. Equilibrium condition is that forces up are equal to forces down. Forces right are equal to forces left. Why? total force is 0, or total force along x and y separately are 0, the same thing. They have to cancel each other. They're vectors, so opposite directions adds up to cancel each other. Last one here is on a tilted surface. Again, it's in equilibrium. The object with mass 1 kilogram is placed on an incline as shown in the figure. What is the frictional coefficient if the object is stationary? Sorry. When you see a system like this, I want you folks to imagine right away. Let me try to draw that. An XY system right in the middle of pattern from the middle of this guy, my object, and take that as your y, and an x that is parallel, parallel to your incline. Okay, not very easy to draw, but let me actually draw them as lines. Maybe that will be easier. So here is my x and here is my y, right in the middle of my object. Okay? So we are tilting our coordinate system for these type of questions. This is y. Up will be this direction for me here for y, and down will be that. Tilted up and down. Alright? And right will be this, and left will be this. And I'm going to apply equilibrium. Up is equal down, right is equal left, or up forces are equal to down forces, right forces are equal to left forces. For equilibrium. Keep that in mind. Alright, so I have 1 kilogram object in equilibrium. It's not moving, it's stationary. What is the coefficient of static friction? Right, it will be static because the object is not moving. What am I gonna do? First, draw an ugly picture, drawn for me, and show all the forces. Or make a free body diagram. Right, showing all the forces. I have mg, mass, always here. And what else do I have? I have normal force, always perpendicular to the surface, so it will be in this direction here, up, right, along y. That's my normal force. And if there's friction, that will be, this object will try to go down and the friction will stop it. So it will be in the left direction in my, let me try that again, system of, alright, for the third time. Okay, this better. And that will be static friction because the object is not moving. For friction, I will always use small f, and if it's static, fs, if it's kinetic, fk. Alright, so I showed all my forces. That's all my forces. Remember, air drag is always ignored unless it says don't ignore it, include it, because it's ignorable, it's negligible, very small for most of the objects we are considering. And friction is always included unless the question says ignore friction. We have friction, we show all the forces. I want you folks to do the second thing. The second thing in an incline is show the components of the weight. See, weight here has an angle with this XY system I put. And this angle happens to be 30, can be proven, but you guys don't need to do it. And for the component along x, because of that angle 30, we will have mg sine 30. We mentioned this in 2D system as well shortly in the video. And this is mg cosine 30. I want you folks to don't say mgy, mgx. It's going to be confusing. Just draw the components of mg and write down what they are in value. Just write down this guy is mg sine 30. Always the component parallel to the incline is mg sine 30. And component perpendicular to the incline is mg cosine 30, or whatever that angle here is. I call it theta here. That's 30. Let me also make that guy theta. Oops, no, not that. Mistakes. Okay, I'm gonna make this also theta. And I'm gonna say theta is this guy here. Alright, show all these first. Then go for it. Then say forces up are equal to forces down. Forces left are equal to forces right. Alright? So I'm going back to question now. I did all that. I'm all ready. What is the frictional coefficient of the incline of if the object is stationary? A. We're doing that. A. Object is stationary. A is 0. Equilibrium. F net is 0. Because if F net is equal MA. Equilibrium condition. Again, we call this equilibrium. Alright? And I say, my system is tilted, but I say forces left. All the forces towards left added are equal to forces right, which means all the forces towards right added. But if you look at here, what I have for forces left is this guy, and what I have for forces right is this guy. So I will say F static friction force is equal to mg sine theta. I know m, 1 kilogram. And mg is 1 kilogram times g, 9.8 meters per second squared. So 9.8 Newton, unit for force. If I use all SI units, kilograms, meters, second, unit is Newton for force. Am I done? No, I'm going to find mg sine theta. Let's find that. Mg sine theta will be mg sine 30. Our theta is 30. And when I put in all my numbers, 9.8 Newton is my mg weight times sine 30. That will give me 4.9 Newton. 4.9 Newton. Now, Fs is equal to that. The static friction force is equal to this guy. I found it. It's 4.9 Newton. Am I done? No. The question is asking me what is the frictional coefficient. It should actually say static friction coefficient, right? Because it's stationary. So let me add that. Or coefficient of static friction as it is in our book. Let me put it like that. Coefficient of static friction. All right. And we call this mu s. So we're looking for mu s, not fs. How do I find it? I look at my friction equation, friction force equation, and it's equals to coefficient of friction, static in this case, times the normal force. I have to find the normal force now. For that, I will say this. Let me change my color here. To find it, I will say forces up. Forces up are equal to forces down. All right? And in my tilted system, this is up and this is down, mg cosine theta. So this gives me n is equal to mg cosine theta. I already know my mg, 9.8 Newton, cosine 30, and this will give me 8.49 Newton. All right, almost there. Now I'm going to input this dude over here and solve for mu s. To solve for mu s, what I would do, divide each side by mu s, right? Or take it to the other side as division. Oh, no, not that. No, I'm solving for mu s. Oh, what am I doing? Leave mu s alone. So divide each side by n. Or take n to the other side as division. Both work. So mu s, coefficient of static friction, is equal to static friction force over n. I found my static friction force, 4.9 Newton. I should go back to blue here actually to avoid too much confused numbers. Oh no, not that, not that. Okay. I'm gonna delete this and write it in blue too. To make it, oh, delete everything. No problem, no problem. All right, go back to pen. So Fs is equals to mu Sn, divide each side by n again, and solve for mu s. Mu s is equal to Fs over n. We already did this, put in numbers, 4.9 Newton divided by 8.49 Newton. That's mu s. I actually don't have this here. I'm gonna do it in my calculator. So 4.9 divided by 8.49, 0.57 is my answer. Notice here, static friction coefficient, I'm going to check that number again, 0.577, so 58 would be a better approximation here. 0.58. No units, Newton over Newton cancels, so friction coefficients do not have any units. Alright, my friends, that's, oh no, there's a B part, that's not all. Okay, what is the normal force applied to the object is already solved, right? So this part here is actually part answers what is in part B as well. What is the normal force applied to the object? And in this case, mg cosine theta, and we already found that 8.49. All right, now that's all, and I'll see you in the next video.